Okay, so with the reactions we've done up to now, we've been dealing with basically this, where we're giving that some sort of SN2 electrophile, we're doing an SN2 reaction, so we're putting a substituent here, and we may or may not have something else attached here to activate it that we then dispose of with the malonic and acetoacidic. But in the previous chapters, we spent our entire life doing this, which is attacking the carbonyl group directly with a nucleophile. Okay. Well, what happens if I do both? If I have this, and I have this, this is electrophilic. This, as we've just spent the past 3 videos talking about, is nucleophilic. Why can't I put them together? The answer is I can put them together. If I do that, it does exactly the same type of thing that we saw before. It attacks the carbonyl just like every other nucleophile that we've dealt with. This process then gets protonated, usually by the solvent, which in most cases we're going to be talking about water, which gives me this. Now, there's more that can happen here, but just for basic concept, these are reversible steps. This is equilibrium, but this is the phrase, this is the origin of the phrase. If R here was an H, this would be an aldehyde. This is an alcohol, hence the Aldol reaction. This is an aldol addition. Usually when we're talking about the aldol, we're talking about an aldol condensation, which is a little bit more complicated, but we'll get there. It just requires an extra step or two on the end of what we've already done. So, let's talk about that. If I started with an aldehyde, as I said, it would still be an aldehyde when it's over, but what I would have attacked here is another molecule of the same thing. They're not showing you what was the aldehyde hydrogen here is still there on the other carbonyl. But the point is, this is now beta to the carbonyl. So it's a beta hydroxyaldehyde or beta hydroxy ketone if I had done it with a ketone. And the point of this is that all the steps are in equilibrium. So any of them is reversible, and we can drive them specifically using the Chatelier's principle the way we would any other equilibrium. But remember, this wasn't a particularly favorable equilibrium to begin with. We talked about that in the first video in the series, in the early part of your chapter. This is not great. So we're talking about a relatively small amount of this present in the first place, of the entire mixture. In and of itself, this reaction wouldn't work. But, like all equilibria, you deplete this by doing something with it, and you'll get a shift to make more of it. So that same thing will happen here, and later when we do additional things beyond that, the equilibrium will get driven the same way by doing something else to the product. That's the easiest way to drive an equilibrium, if you can, is to do something with the product. You're depleting its presence, its concentration, and therefore the unfavorable equilibrium that might have made it suddenly has to shift to make more of it. So, a few basic principles. Ketones don't work very well. Why? Electronically, they're very similar, but look at the approach. This is not easy. It's bulky. It's more difficult of an approach, so it's not great. Not to say it can't be done, but it's not nearly as simple as doing it with an aldehyde. So that's worth keeping in mind. This is more of a problem with an aldehyde. If this is not the reaction you wanted, you got to be really careful with conditions, and this is where base strength and things like that come into play. If I wanted to do a regular enolate reaction, this is not the base I would use because it's too slow and too weak, and I end up with something I didn't really want. My own impression, possibly mistaken, is that this is probably how the reaction was discovered in the first place. Is somebody doing an enolate reaction, but doing it weakly, and ended up causing an addition, which turned out to be extremely useful. So this might be a very famous version of making lemonade from lemons, a reaction that doesn't work well. Okay, so we're not worried about the retroaldol. What we generally see, though, in a lot of cases is the alcohol gets lost. We end up with an alkene here. And it's not generally a second reaction in terms of having to change the pH of what they're suggesting here. The aldol is typically hydroxide as the base, and then, if we're not careful, we end up with the alkene, which is in many cases desirable. We have some uses for those we'll talk about later. How? How did that happen? So, how did we get there? This is what's occurring, the overall loss of water. But if I'm in basic conditions right here, how am I losing water? The only time we've lost an OH group at all, we had to protonate it first. That's not possible here. It's actually the most common mistake when I have people draw a mechanism like this is they tend to try and protonate things when you're in basic conditions. Let's get that out of the way right now. You cannot use a hydronium ion to do anything with if you're in solution with sodium hydroxide. That doesn't work. Okay? So, be careful with that. Don't get stuck with that one. So, here's how it actually works. We've already done part 1. We don't need to talk about that again. You can rewind the video and watch that if you want. Part 2 is different. We're forming a second enolate. That's what this is a second enolate. But then we're losing a leaving group. Specifically losing a leaving group that I told you up and down is not a reasonable leaving group. Because it isn't. It comes up only 2 places, and only one of them your book talks about is right here. The other one is the Wolff-Kishner reaction, which requires higher temperatures to manage it, because it's an unfavorable leaving group. This doesn't require brutal temps to do. So what's changed? The OH is not being protonated. Let's get that out the way real quick. This is not ever here. We are not making that leaving group. We are not protonating that alcohol. We are not creating water as a leaving group. What's lost here is the hydroxide, not water. Don't get it twisted. This is not a good leaving group. This is. If we had protonated it, the leaving group's easy. That is not what happens in sodium hydroxide. Thou shalt not protonate things with sodium hydroxide. It's not capable of it. Okay. So, we occasionally have to worry about stereoisomers. That's a minor problem, but generally, again, just like regular alkenes, we're looking for the elimination to have less steric problems, so trans is generally better. If we have something that's going to make that leaving group even more favorable, well, then we're probably not going to be able to catch this. And that's the case in a lot of useful examples of this reaction. We're forming a conjugated system. So let's go back and say that for a second. This is conjugated. We now have a 4-pi system. So, again, this is a 4-pi system. This is favorable. And now we're looking at conjugation all the way across here and into here. So we're looking at a conjugated system that's massive. So of course it's going to be very favorable to form that pi bond. It completes conjugation across the entire structure. So you'll never see this. You'll never see that alcohol. It's going to be there and it'll be gone even faster. So the elimination here would be massively quick. Normally we have to work at it a little bit. The ketone, as we said, doesn't work particularly great, but if you hit things hard enough, you can make them work. So we crunch up the temperature a bit, and yes, it will work, but not to form this. We're still not seeing that. It has to form along the way. We're getting to that. But we're under conditions where the temperature and the energy in the system makes the elimination much quicker. So we can get good yields of the aldol condensation. We just can't really get a decent yield of just the addition where we stop it with the alcohol present. All right, it's a limitation, but not a deadly one. Okay, so behold the absolute worst experience of my entire teaching career when it comes to an exam question. I asked something very, very similar to this, and I took more garbage over that from the class than anything I've ever written in my life. It was a very interesting learning experience. That semantics are really worth playing with if people are going to be a pain in the tail about it. So, here's the problem. If I try to crisscross and do an aldol reaction with ketone A, or sorry, aldehyde A and aldehyde B, the idea being that I want basically this. I want one specific product out of it. I'm not going to get it. We're using a weak base comparatively, which means I've got equilibration. Translation, one enolate forms, goes back, potentially forms the other one. So I have to deal with two different enolates and two different aldehydes. So I have every possibility here. First one, this is A and A minus. Second one, this is B and B minus. Then I've got A and B minus. Then I've got B and A minus. So I have a reaction that gives me 4 different products. Now, to me, being young and dumb at the time, I don't consider that a reaction that actually works. If your product is not the major one, then that reaction is junk most of the time, and this is one of those cases. So I wrote a question saying, does this reaction work to give you the product you want? Statistically, no. Consider your yield of any reaction to be a grade. If you're below 60, that's a failure. Okay, so I view reactions much the same way. Unless there's a legitimate reason, like ortho and para substitution, where you can't really separate the two isomers mechanistically, a reaction that gives you a mixture is not a successful reaction. So I had to actually argue quite a lot with that. And so when I used this question again, I had to say, does it work cleanly? Will it give you a clean product of the one you actually want? And the answer is hell no. Statistically, 25%. Sterically, probably even less than that, because this will be slightly easier. So you're going to have a mess. And the one thing you don't want is to make multiple compounds in a reaction that are very, very similar in functional group terms. It means they're probably going to be very, very difficult to get apart. The effort it would take me to get this out is going to cost me much more time and much more money in chemicals than it did to actually do the reaction in the first place. To me, that's a failure, a big one. If it's the only way you've got, well, you suck it up, but it's not. There are other ways to go about this. There are ways to beat this that we haven't talked about yet and may not in this course, but the point is you don't have to take a loss to a reaction that gives you mixtures all the time. Again, ortho and para, you don't always have an option, but when it comes to something like this, we can go about making the enolates different ways to control which one's present and then which one can be attacked. We can beat this, but not using the conditions we've talked about so far. So the conditions as written here, those two functional groups, those two aldehydes together with sodium hydroxide, this is an ungodly mess and you wouldn't want any part of it. Unless you just hate yourself, at which point, I don't know, go bang your head against the wall, because it's basically the functional equivalent of doing this reaction and hoping for one product. All right, so when is it going to work? 1, if you can't form a second enolate, well, you have to have alpha protons to be an enolate. It doesn't have any. It has no alpha carbon to have protons on it. So it's not doing anything but getting hit. So it is the substitute, it is the electrophile. It will never be the nucleophile in this process. What I would have to do, though, is I'd still have to make sure I have plenty of base on this so that I don't end up with that attacking itself. So it's still a little trickier than they're implying here. But we can do that. It's just a matter of stoichiometry at that point. I want this to basically be 100%. So I'll probably use large excess of this because it's not doing anything to this. There's no protons to deprotonate. Those hydrogens are not acidic at all. So I have no worries about sodium hydroxide doing anything useful to that structure. The other case, Again, no alpha protons, but it's much more useful if I have aromatic rings 1 or 2 there. So we'll see this quite a lot using benzaldehyde, which is what the structure on the left is, or aromatic aldehydes, because that gives us a conjugated system here, which tends to be fairly important in a lot of contexts. So we have a lot of uses for that trick. But again, same idea. We have one component in the reaction that can't make an enolate, period. Okay, so how can we get around this? I'm surprised your book did go here. All right. We basically overkill one of them. We make the enolate specifically with a strong base, then there's no equilibration. And then we add this to it. But even there, we got to be a little bit careful that we don't just dump it in there. We want a lot of this with a little bit of this at any given moment. So this is going in slowly. The idea is that for every one of these that hits, I want a whole bunch of things to attack it really quickly before it can decide to equilibrate. So I want it out of the game before it has a chance to form an enolate by equilibration. So addition rate here is critical to make this actually work. Once you get past that hindrance, this reaction is pretty straightforward, and it can be done. It's more tricky than what the previous slide showed, but it's not impossible. It's not as easy as just dumping sodium hydroxide in. That's relatively simple, and it's going to require lower temps to make the enolate, and your addition is going to have to be careful, and your temperature control is going to have to be good. So it's more experimentally challenging, but as I said, most of the time you don't have to take a loss with mixtures the way that the previous slide suggested. You can beat it with conditions and with temperature. Okay, so next up, intramolecular cases. Can I close this down into a ring? That's a really useful thing if I can do it. But limitations. It's not going to work if I try to form something too small because of ring strain, because of angle strain of the transition state before the ring forms. It's not going to work if I try to form something too big because I'm looking at too much entropy. The groups would never fold back on each other if there were too many ways for them to rotate apart. So basically we're looking at a case where this only works if I'm going to find 5 or 6 membered rings. It does work with 7s, but not great. And above that, it really is not worth the effort most of the time. It's too slow. Below that, it's just not going to happen. You're not doing a reaction to form a 3-membered ring this way. So there's our question. Now, your book here has shown you the one that gives this product. So that's forming an enolate here and attacking there. Well, it's possible to form an enolate there. But if I did that, I'd have a 3-membered ring, which ain't going to happen. So the other way of doing it, starting from here, of course, forms a 5-membered ring. So if I'd done that from here and counted them off, there's 1, 2, 3, 4, and 5. So with this being 1. So, and this being 2 in the final structure. So we can go about this with limited cases. This works with aldehydes, this works with ketones. We can work with, to form 5 and 6 membered rings pretty readily. Now, there is a version of the aldol that works with esters. It is slower and has some other issues that we're going to talk about as we go along the way. It's called the Claisen condensation. In this case, there is no hydroxy product because we're taking advantage of something that we've already done with esters back previous chapters. So here it is that if I took a nucleophile and used that with an ester, in the case of doing it with a ketone or an aldehyde, I get an alkoxide, which then basically most of the time leads me to an alcohol when it's over. There's not really anything else to do here. But if I do that same trick with an ester, I get the first step is exactly the same. Tetrahedral intermediate, no pi bond, and nucleophiles attached. But then I have a leaving group here. So carbonyl reforms, leaving group goes. Depending on the nucleophile, this may end up having another nucleophilic attack. That's what happens with Grignard reagents and hydrides. But the point is, the difference between the aldehydes and ketones is here. I do not have a leaving group here, which means I'm not doing anything else, really. I do have a leaving group here. So I can reform that carbonyl, and that is going to be the biggest part of the Claisen that is different from the aldol. So we're forming a ketone here because in the intermediate stage there was an ester, that. And it got, that ethoxide will get thrown out to reform that particular carbonyl as we go along. So here we go. Our base needs to match the ester. So our base needs to match the ester. Otherwise, we hydrolyze the ester. Pointless. Doesn't help us. So if this is an ethyl ester, we use ethoxide, methyl ester most commonly. Methoxide is the base. Nothing magical about that. It just happens to be easy to make and cheap. So we could use different esters and different bases, but you know, we could also waste money on other ways. So we don't, generally. But here's the difference. The aldol looks just like this. Enolate attacks carbonyl group, breaks the pi bond, we get to a tetrahedral intermediate with an alkoxide. Here the difference is I have that leaving group. I didn't have that before. So now the carbonyl reforms, leaving group is gone. But that leaving group happens to be the original base. So I now have an alpha carbon between two carbonyl groups. That's very acidic. So that's going to get deprotonated and it's going to stay there. This is what actually happens at the reaction. It's an equilibrium, but it's a really favorable one. So this basically stays until the end. But it changes one thing. It kills off the base. So the aldol, we get away with using a catalytic amount of base. A very small amount of base because it gets regenerated at the end. In the aldol case, we had this, and then that enolate that we formed at the end would blast that out. And so I get this back at the end. I get my base back, and then it goes back around to do the aldol again. That doesn't happen here. Here my base, the last molecule of base is right here. It gets eaten up. It gets used, and this is not a base. Not on the terms we need for this reaction. So we have to use a full amount of base here to get this reaction to work. So that means this and this are a 2-to-1 ratio. Okay, why 2-to-1? Because I need one of these and I need one of these. So I can only deprotonate half of it. So I need 50% base. By moles, I need 50% of that relative to my original ester so that I get 50% enolate and 50% not enolate, or still ester. Otherwise, my reaction is not going to go to completion, or I'm going to get lower yield if I don't carefully manage the stoichiometry here. Okay, after the reaction, I still have an anion here. So the only way to get the actual product out of this is to treat it with acid as part of the necessary workup. Now, usually that happens in something like a separatory funnel. This is dilute. This does not require any strength to it. We're not looking to cause any other problems here. This is usually something like, 1% HCl or something. Not strong acid, but enough to take out any leftover base, if I didn't measure it correctly, and enough to protonate any leftover anions. So this is part of the last step. It's not part of the mechanism. It's part of the workup. So this is after the reaction mechanism is over because I didn't get a neutral product. I got an anion as my product. So to get to a final neutral product, I need to add something more acidic than an alcohol. Can't use hydroxide. As I said, your base needs to match the ester because otherwise you're going to hydrolyze this, and this is not making an enolate. No enolate. Ever. Why? Because this is a resonating anion. If I form that, essentially I'm looking at a negative charge, a partial negative charge, right next to my alpha carbon. That does not make things acidic. So a resonating carboxylate would actually make it much more difficult to form an enolate, essentially impossible. So if we do something like this and hydrolyze the ester, we shut down the Claisen entirely. Second, there has to be 2 alpha protons. The reason for that is that over the course of the mechanism, if we go back, we're pulling one of them here and another one of them here. So there are 2 spots, the original enolate and the next enolate that forms at the end, where I have to pull off the same carbon. So I have to have 2 alpha protons to make it work. Okay, cross Claisen, same problems as before. We don't want multiple different enolates, so we basically want to make sure one of them can't form it, which means we've got a couple of examples. We've got a formic acid enolate, a formic acid ester. We've got the benzoic acid ester. We have a benzene. Again, no alpha protons, no ester is possible. Otherwise, we have to play games with the condition, just like we did when we talked about the crossed aldol. Form one enolate first with a stronger base, and then with temperature and with careful control of the addition, then put them together so the equilibration doesn't give you mixtures. Okay, intermolecular version of this, very much like the cyclic aldol, called a Dieckmann cyclization, but we don't have any possibility of deprotonating 2 sides. There are no 2 different enolates possible around the carbonyl group if it's an ester. There's only one side to work with. So here, we don't have really that many options. Again, 5 and 6 membered rings good, larger, problems with entropy, smaller, problems with angle strain coming into a transition state. So very unlikely that you're going to form something that would end up with a strained ring. Mechanistically, it's exactly the same. Deprotonate one, it attacks the other. There's no difference in the cyclic version mechanism to the original one, just the 2 pieces are tied together. So basically you're looking at, an enolate, this is the cyclic version. I have an enolate here, but instead of having something external, it's just tied to another one. It's tied to the actual electrophile. That's it. So this line here could be used if I go back and say, all right, let's go back to look at the original one. If these were tied together, so if this were already attached like this, then you're talking about a Dieckmann cyclization. If I have attachment between the enolate carbon and a chain between that and the ester itself, then it's intermolecular, you're forming a ring, it's the Dieckmann